All right, good morning, good afternoon. This is going to be a quick little flip lecture video for October 29th and 30th. Today's focus is going to be over chemical equations and chemical reactions. In this situation, I do need to preface a few things related to Unit 3. In this case, when we're going through Unit 3, we're really going to focus our main effort on chemical equations. We've seen these a little bit when we've gone through Unit 2 in nuclear decay. In this case, we're going to be looking at the full process of a reaction. So we're going to have some sort of material. We can have material A reacting with some other compound, so SO for some other, and it's going to form some sort of product. This is what we're going to be looking at in terms of chemical reactions. We are going to look at the five main types of chemical reactions within this unit. A lot of this is going to be redundant information. It's going to be a lot of practice, so don't worry too much. The only parts that are really going to be a little bit of a refresher is related to balancing equations. We've looked at this a little bit when we've talked about compounds and counting atoms. So in this situation, we're really just going to be balancing the amount of material that we have in a given reaction. The main area that we're going to focus on today, however, is really going to be the chemical equations as well as balancing equations. This will be the same case as we go through the rest of the week as well as on to next week in early November. But in this case, we're really going to be looking at the balancing aspect in a lot more detail. So with that in mind, today's goal is really just to further interpret what a chemical equation is. We're going to look at each of the components, including products and reactants. So main focus is on our reactants and products. Because in all actuality, a equation is just telling us a process. It's telling us some sort of story. In this case, we start with something and we end up with a completely new substance afterwards. That's our focus for today. We're going to focus on the components, mainly identifying what is a reactant, what is a product, and what are each of these random symbols that we're going to start to learn, like AQ in parentheses. What does this arrow signify? That is our primary goal for today. With chemical reactions. When we look at a chemical reaction, it is always going to involve the overall change of a substance. In this case, we recognize a chemical reaction as reactants change into a product. This is the entire formula process. This is what we're looking at when we're diving into the aspects that is a chemical reaction. When we look at a reactant is simply a substance that is present before an overall change occurs. In this case, it'll be written on the left side of our equation and or reaction. When we look at a product, this is going to be present after a change. In this case, it'll be on the right side of your equation as well as your reaction. What we'll recognize when we move on to an example here in a moment, we will recognize that all of our reactions are written in a pattern sequence. In this case, you always have a reactant moving towards a product, further emphasizing the fact that we have reactants that change into a product. This little arrow here signifies what's called a yield arrow. A yield arrow is just signifying that a change has happened and we've ultimately formed a new product as a whole. The direction of that arrow, in this case, I have an arrow that's going to the right, just signifies where my reactants are compared to my products. As a reminder, by definition, we recognize that a reactant is something that is present before the change occurs. Products will always be after. So reactants will be at the back end of the arrow. Products will be at the arrow head. Okay. One way that I learned chemical reactions, further emphasizing my background in nutrition, is the fact that we can really look at this as creating a meal. In this case, whenever you're looking at cooking a meal for yourself, whether it's ramen noodles, whether it's grilled cheese, you're recognizing that you are starting with some sort of material, some ingredient to start with. But as you go through the process of cooking, you eventually create a final product. So in this case, if I'm looking at an example of a grilled cheese has reactants or ingredients that include cheese, bread, and butter. If you want to keep it plain and simple, your final product, whatever you make through the process of cooking, is going to be that grilled cheese. So, something to think of whenever you're looking at chemical reactions as a whole. You can think of it as cooking. You can think of it as making a project, like if you're clay sculpting or anything of that nature, something where you start with a material but end with a finished product. Okay, this slide is really just emphasizing the three components that we've looked at so far. We have looked at our products, our reaction arrow, as well as our reactants. So, in a situation where we're making a compound known as sodium chloride, your table salt that you guys commonly will season your food with, we recognize that it did not start as a full-blown compound. We had to have two individual ingredients, our two elements, that of sodium as well as chlorine, as they are combined together through what's known as a synthesis reaction, we create our final compound. We create that structure known as sodium chloride. So in this situation, I will recognize that my reactants are always present before the arrow. In this case, they're always present before any overall change. Our products are always going to be present after a change occurs. So in this case, I recognize my products are after the arrowhead. My reactants are prior to that. Then we have our good old reaction arrow. I use this description often to describe what this arrow signifies. In this case, we're looking at the overall direction of change, as well as what we are creating. So that's why we recognize it as a yield arrow. In this situation, we are simply looking at the story that is written, taking our reactants and forming or yielding an overall product. So one of your guys' assignments that you have today is really looking at chemical equations, but identifying the components through a recipe format. You may see the grilled cheese example again. I gave it to you guys for an example because we're going to recognize that a lot of our reactions will have a limit to them. We could be given 2Na as well as 3Cl to form NaCl. In most situations, we're going to take one atom of sodium and one atom of chlorine to form that compound. Sodium chloride is simply one sodium to one chlorine. So in this case, if I have two of them present for sodium and three for chlorine, I will have enough to make two compounds with one extra chlorine atom present. So this assignment, I want you guys to take about 10 minutes, work with those sitting next to you in your pods. In this case, I want you guys to focus solely on this assignment, so don't continue with your notes. I only want you to spend the next 10 minutes working on this worksheet. If you get it done, great, turn it into turn-in tray. If you don't, hang on to it for later. So take 10 minutes. Okay. Something that we need to review before moving on to balancing of chemical reactions and chemical change, we need to recognize that we have those five main signs. As we move into types of reactions in the future, we're going to recognize that a lot of our products will have each of these components. Maybe they'll have like a light or flame. They may produce a gas at any point in time. They might have a temperature change. We won't see all five in every reaction, but we may see one or two. So over to the right-hand side, I've given you guys a couple of examples related to chemical change. In this case, we're looking at lighting a wick. In this case, the very end of a match. We recognize that by involving a temperature change, we have formed an overall flame, as well as light. Formation of gases. This is one of our many forms of phase change that we recognized in Unit 1. In this case, we're taking a liquid and turning it into a gas. This involves a temperature change. In this case, we have to add in thermal energy to get this overall system moving. Next, we got a color change through the decomposition of different leaves. So as we move into the later part of Unit 3, we'll recognize this as a decomp or DEC. This is a decomposition reaction where we have a compound breaking down into smaller parts. Over here in these vials, this is what's known as the formation of a precipitate. In this case, a solid substance forming from the mixing of two liquids. The last piece that we have is an overall temperature change. You guys have probably experienced this every single day of your life, but if you were to maybe walk around, move your body, burn calories, those calories are given off as heat in most circumstances. Our body gives off that heat through sweating, which is a way for us to cool down our body. Our human bodies are a constant chemical reaction, whether we're balancing what's known as pH, which is dealing with acids and bases. It could be the breakdown of sugar into ATP, adenosine triphosphate, which is an energy source that we can use to walk, run, talk. It's truly up to you. In all those circumstances, we are going through chemical change. Could be a temperature change, could be a color change, formation of a solid, formation of a gas, or the production of a flame and light. Let's go ahead and talk about chemical reactions in the sense of actually writing these detailed stories. First thing that we need to recognize, kind of dividing my page in two, is that when we're going through any sort of reaction, we are going to recognize the physical state of those substances. We did this early on in Unit 0, as well as within Unit 1, when we talked about phase change, in which I gave you guys the first 3 states of matter that we recognize within a chemical reaction. First off, we recognize our solids, our good old cubes. These cubes are very dense. They have a defined volume to them. Then we move to our liquids. In this case, they aren't necessarily going to have a defined shape. It's truly dependent on the container. And lastly, we got our gases. Our little friends that like to run around, play, and do whatever they so wish in any sort of direction they would like, at any sort of speed that they would like. Then we move on to a new area. This is aqueous. So aqueous is simply something dissolved within water. Typically, it will be a solid that has been added to a liquid, as a result, creating something that is aqueous. So think salt and water, for an example. We know this to be what's called an ionic compound, or in this situation now, an ionic solution. In this case, we're going to recognize that the solid particles that is table salt will dissolve into water. So with that kind of basis, we're going to eventually add those in to our reactions to describe what is actually happening in greater detail. So moving to the other side, we recognize that when we're looking at a chemical equation, we're recognizing a direct relationship of substances that are being used either as a reactant or formed as a product. So in this case, we're going to bring back our suffixes, not suffixes, our subscripts, as well as our coefficients. As a reminder, these are numbers that we place in front of for coefficients and down to the bottom right for subscripts. So we recognize our coefficients as being our compounds. In this case, we're recognizing how many of a certain mixture of elements are present in a situation. So in this case, when I look at 2H2, I recognize I have 2 compounds of a diatomic hydrogen. In this case, I recognize that they are in a gas state, given that they have the percent, well, parentheses G next to them. I then recognize a second one of my reactants as a diatomic molecule of oxygen. So in this case, I have two oxygen atoms, in this case in a gas state. Then I go to form a product that is that of water vapor. In this case, I have two molecules of it, consisting of a total value of two hydrogen to one oxygen in a compound. As we go through the rest of this lesson, we're going to learn why we put these coefficients in front of our compounds and really what their significance is. So before we get to talking about those coefficients and really understanding why it is that they're there in the first place, we need to really go back to Unit 2 for a second. We need to relearn how we count the amount of atoms within a compound. This is going to tie in coefficients as well as subscripts in order to determine the amount of atoms that we really have. So, really quick, let's go ahead and look at our equation to the left-hand side, consisting of a methane molecule as well as diatomic oxygen producing carbon dioxide and water. We haven't specified whether these are solids, liquids, or gases, or even if they're aqueous, so we don't have to worry about that right now. In this case, I'm going to go ahead and break this entire kind of text area into two sections because I am being asked to label the reactants and the products to begin with. So in order to do that, I just need to look at my yield arrow. I need to recognize what direction it's going in and where our components are. In this case, prior to the arrow, I recognize I have the CH4 molecule as well as O2. This is going to be my reactant because this is what is present before an overall change. Anything present after that change is my product. So I recognize CH4, 2O2. Those are combining together to then produce CO2 and H2O. Now that I have that out of the way, I need to go ahead and specify the number of each element on the reactant and product sides. This is going to be a really good skill to have, especially next class when we dive deeper into what's known as an RAP table or a RAP table. This is what we're going to use in the future to really investigate how much material we need in a given equation. But before that, let's go ahead and do some counting atoms. I know I have carbon, I know I have hydrogen, and I have oxygen on both sides of my reaction. Both the product and reactant sides have the same material. Let's go ahead and determine how many of each atom is represented. Let's start with our reactant side. I recognize with my single atom of carbon, I have no subscript. Whenever I'm given an element with no subscript, I recognize there will only be one atom. Because we can never have nothing of something, we are going to always represent an element with no subscript as really just being one atom. Now, I look at my hydrogen. Hydrogen on the reactant side has a subscript of 4. That tells me I have 4 atoms of hydrogen. Last we have is oxygen, O2. I recognize, given the fact that I have a coefficient present, I have a number before my compound, whatever I have in one compound of O2, I will double, given the fact that my coefficient is 2. So in this situation, I recognize by having a subscript of 2, I really have 2 atoms present per compound. So in all actuality, I need to now multiply it by its coefficient to get the full value of oxygen atoms, which is 4 oxygen. Okay, let's do the same thing for the product side. In this case, I'm going to start with carbon. Carbon, again, does not have a subscript, so I have one atom of it. Hydrogen, on the other part, I recognize is split into two compounds of diatomic hydrogen within a water molecule. So, similar to how I did it with my oxygen over on the reactant side, I'm going to recognize how many atoms I have in the compound first, then multiply it by its coefficient, in this case of 2, meaning I have 4 atoms of hydrogen. Last piece that I got to solve. In this situation, I need to count up the total amount of oxygen, but it's in 2 places. I have it in my water molecule, and I have it in my carbon dioxide. So we're going to do a little bit of addition. I know I have 2 atoms in the carbon dioxide molecule, given the fact that there's a subscript of 2 to the bottom right corner of my oxygen. I'm going to add this to the amount that I have within the water molecule times its coefficient. So in this case, it will be 2 times 1. Its total value in this case will be 4. Let's look at something that's in common here for a second. I recognize that I had 1 atom of carbon to start with. After the reaction went through fruition, it completed, I still had 1 atom. Hydrogen as well. I had 4 atoms to start with. I ended up with 4 atoms to end with. In this case, my product in all circumstances will have an equal amount of atoms before and after the reaction has happened. So I'm going to skip over this second example, looking at a glucose molecule reacting with oxygen. If you need extra practice, please let me know. We can go over this equation together. But with that being said, I'm going to skip that second piece, and we're going to talk about the last major component of chemical reactions. In this case, we're going to look at catalysts. A catalyst is really something that is going to be added to the reaction mixture, but is not used in the reaction whatsoever. Its purpose is really just to make things faster, either to decrease the temperature needed for the reaction to happen, maybe to increase the amount of energy that is in the system in the form of heat. Catalysts are always going to be a substance or an energy source that we provide to the reaction for it to be faster. So when we look at a catalyst within our chemical reactions, they will always be provided above your yield arrow or your reaction arrow. So within our reaction, when we're looking for our catalyst, it's really going to be above the reaction arrow. In this case, I have MnO2. This is a permanganese compound. In this case, we're recognizing it is producing a reaction in a quicker speed, where we're recognizing H2O2 is breaking down into liquid water and oxygen gas. The only purpose of this compound is to make things faster. You'll recognize it's not a reactant, nor is it a product. It's just a substance that is provided to simply speed up the reaction. So, last little summary slide for you guys. We're really just going to look at each of the kind of symbols that we find within our reactions. So, first area I want to start with, since we just talked about catalysts, there are really 2 main types of catalysts that we're going to see within this section of physical science. In this case, we're looking at the addition of heat as well as the provision of a kind of a substance as a catalyst. In reality, this is just providing how much material or energy is given for the reaction to speed up. But I do also need to preface. Within our reactions, there will be a few types that we recognize that can produce as well as need heat to actually happen. So in this case, I recognize that heat can also be something that's supplied as well as produced within our given reaction. Now we move on to aqueous. Aqueous, we just designate it as a substance dissolved in water or in some other solution, excuse me. A solution is really just looking at a liquid substance. Then we have good old solid, liquid, and gas. These symbols we have looked at already in the past. We described phase change using these symbols. Then we have a very wacky version of a yield arrow. This is what's known as a reversible reaction arrow. So you'll recognize on both sides of the arrow, top and bottom, we have one half of an arrow going to the right. We have another half of that same arrow going to the left. This is just saying that whatever I produce in the reaction could also be used as a reactant to produce those starting materials. Then we have our good old yield arrow. And remember, this is just the kind of conductor, so to speak. It tells us where our reactants are and where our products will be, just so we have an overall story. Then we have an addition symbol. We don't really recognize this as being an add situation. Only when we're looking at a reactant will that be a kind of situation where I'm adding these two substances. Whenever we're looking at it on the product side, we're just recognizing that we have two different components. So these are the main symbols that we need to recognize when we're looking at the components of a chemical reaction. Before you guys freak out, assignments wise, when we're looking at the assignments for today's class, you will recognize right off the bat that you've actually already started one. You're about to finish it. So if you took the 10 minutes during the notes to actually focus solely on the chemical equations with recipes assignment, you will have most of that completed. The next one, which you can do at home, is a demo worksheet. So this demo worksheet is going to get you guys prepared for about a week from now. We're going to look at chemical equations and the types of equations. This will give you guys a visual to recognize that chemical change still happens within any sort of chemical reaction. Then the last one. These should hopefully already be provided on Schoology for you. I didn't have a printout made quite yet. I didn't expect to be out of the building for so long. But in this case, you guys will also have another station rotation. You can treat this as a worksheet if you so choose, or if it's already set out for you as a station rotation, you'll just remember that you have about 7 minutes per station. So try to rotate as much as you guys can. If not, that's perfectly fine. These are your guys' assignments. Again, just going back through it. This recipes assignment you should have started within your notes. So you have that to begin with. You're just looking at equations in terms of cooking recipes to give you guys some sort of analogy. Then you have your demo worksheet. This is a worksheet, kind of like a lab. In this situation, you're going to look at different experiments that are done for you and just recognize what types of reactants and products are used, as well as doing a little bit of counting of atoms. This last piece is a practice. It is still an assigned practice, so it has a grade. But the due date for this station rotation will be in November. If I recall correctly, it's November 3rd. So you guys have a bit of time to get this one worked out. Focus on the demo and the recipes worksheet for today. So if you don't get to this last part, that is not a problem at all. This is something that we could use as further practice in the future. So if you guys have any questions at all, please feel free to email me. My email box is open still. I've been trying to email back students that have messaged me over the past couple of days. So if you have any questions whatsoever, especially if it's over your guys' Unit 2 exams, please send those emails and I'll be sure to get back to you at any time.